Hi everyone. Today I'm going to introduce you celebrate Black-Scholes formula. This formula lead to the boom on option trading and lead to huge impact on theory of stochastic processes and financial theory. I'm going to show you how we can get this formula from Cox-Ross-Rubinstein model using log normal approximation. But first, about the previous lecture. You remember that we assume that T represent the duration of the contract in years, N is number of equals periods between trading dates, dt duration of each period, R capital denote the continuously compounded interest rate, and R little is interest rate for one period. And at the previous lecture, we introduced and considered the variables y equals 1 divided by t, logarithm st divided by s0. It is log returns for our data. And we construct the binomial tree according to the rule that the next value s sub n equals the previous value multiplied by u if the price goes up, or multiplied by d if the price goes down. And we used the very useful formula. It's formula that log returns we can represent as the sum from 1 to the n logarithm of Sn divided by Sn minus 1. And we assumed that these increments are independent. After that, we can find mathematical expectation of this logarithm's growth rate and the variance. And we have the next system of two equations. In this equation, you can see that we have parameters of these trees u and d, and probabilities, it is risk-neutral probabilities qu and qd. But what is mu and sigma square? It is trend of our real financial data, and sigma is volatility. How we can find estimates of these parameters? We can take real financial data, for example. For example, we have real financial data for some period, for example, 1 year. We can this on the graph, and we have this as series: S0, S1, S2, S3, and so on. And from this data, we can get the next series from its log returns. The first value will be log S1 divided by S0. The next log S2 divided by S1 and so on. And the last value log Sn divided by Sn minus 1. And for this series, we can find the mathematical expectation from these values and variance. Mathematical expectation and variance. And this mathematical expectation is estimates mu from u in this equation. But volatility, this volatility, it's for a day, 1 day. But in this equation, this volatility for 1 year. So if we have, if you would like to have volatility for 1 year, we should this volatility divided by the delta t, but in really it is multiplied by 242 because it is number of trading days in the year. So we can get the estimates from volatility. And so we have this value from real financial data and this value from real financial data. But we have 3 unknown variables. It is Q, QU, U, and D, but because QD equals 1 minus QU. So we have 2 equations. We have 2 equations, but 3 variables. And in order to solve this system, we should to make some assumption. It is or method of symmetric probabilities or method of symmetric limits. In the first case, if this probability equals 1 divided by 2, the solution of this system will be as follows. But if we apply the method of symmetric limits, its method it is that d equals 1 divided by u, the solution of this system will be as follows. Do you understand? Is it clear? Sophia?
Yes. Yeah.
Thank you. And next, this fact we take without proof that if the limit dt more or less than 1, the risk neutral expected growth rate is the function of the interest rate and the volatility. Mu approximately equals R capital minus sigma squared divided by 2. Do you remember that it's it is volatility, and it is interest rate for 1 year. And now we can build a binomial tree. We can find U and D. If we know from real financial data that volatility is 10%, for example, and interest rate 5%, and our task to construct a binomial tree with 20 periods to value a 3 months investment. So solution will be that dt equals 0.25 because it is 3 months duration, and divide by 20 because we would like to consider exactly 20 periods, and it will be this number. And using the first method, we have that u equals exponent to the power of this expression, and we substitute volatility 0.1 square root from dt, it is this value, plus r, we have r, it is 5%, and minus volatility square divided by 2, and dt is computed up. So we have that u equals 1.0118, and after that we can compute d, and it will be 0.98944. So we can construct this binomial tree for if we have that initial price 100, and now we know u and d, and we can construct this binomial tree. If number of periods n tend to infinity, then binomial parts will look like Brownian parts. So it is in really, but it's model for this case, and we have these three trajectories, and it is as this on the binomial model. And now we would like to consider a log normal approximation of this Cox-Ross-Rubinstein model. So we would like to consider continuous variant of the discrete model. For this, we should apply the approximation, and it is dt goes to 0, or n tends to infinity. And you remember the log returns. It is 1 divided by t logarithm of this Sn divided by S0, and very useful to present this as sum of 1 to the n. We can denote every term in this sum as hn, and so we have that this logarithm is the sum of h sub n, and after that we would like to apply a central limited theorem. Maybe you remember this theorem for the theory of probability. Yes, you finished this course, and um, this theorem states that the sum of identical independent contributed
Distributed.
the,
Independently distributed in the, no.
independent distributed and dependent yes and dependent variables tend to its mathematical expectation and the distribution and law of the distribution. It is normal distribution and mean and variance you see. And from a theory of probability, we know that if we have the random value with normal distribution with parameters a, it is mean and its variance, a and b square, then we have considered transformation in transformation which looks as this, and it will be normal distribution. So from this we have that x minus a equals z multiplied b, and x equals a plus zb, whereas z is standard normal distribution variables. So in our case, this log returns, which is the sum of n values, and if n tends to the infinity, we have that it is mu t, because mu t it is a plus z, that it is standard normal distributed value, and multiplied b, and b it is sigma square root from t. So we have a theorem that the distribution of Sn convert to the log normal distribution, and which looks like this. And it's very important because it's model for stock for our stock movement. So we have that model for risky asset, and now we would like to get the formula for fair price derivative, and more in our case for in our case for call option. So let dt tends to 0 and n to the infinity. And what is fair price of derivative? It is discounted mathematical expectation of your function respect to risk neutral measure. Yes. In approximation case where dt tends to 0, you know that it will be exponent to the power minus r capital T capital. So from this we get this, and we should substitute this expression as SSN instead as SN. This expression we got on this slide, yes, and we write that fair price of call option equals this we write, but what is mathematical expectation in the continuous case? Maybe you remember from theory of probability that it's integral from value multiplied multiplied by measure. Uh, the value it's for your function. What's for your function? It is the market price minus strike price. Market price in the time t capital according to our theorem, it is this value. But risk neutral measure, we mentioned that it is the normal distribution. So it is a measure of normal distribution. It looks like this. But but you know that call option it's contract which it's contract contract which wins where the market price more than K. But at the opposite case, the your function is zero. So we write that it is some value. We can denote this minus d2, but now we don't know this value. But above this value, it's our win. But less than this value, it's zero, only zero. You remember. And then, what is then? Um, we we rewrite this as the sum of integrals. This multiplied to this minus k multiplied to this. We rewrite this, and this factor we write after under integral. And now we should to find this integral. After that, we replace a new variable u, which looks like this. Du equals dz, it's clear, and d1 equals minus d1 equals minus d2, or maybe d1 minus sigma square root from t. Why this replace? Because you see that it is the square root from the sum. It is and if it will be the low limit, so after this replace, it will be this limit. Yes, minus minus. And you see that this we can rewrite. You see that we can rewrite this e exponent to the power and minus r t plus z sigma square root from t plus rt minus sigma square divided by 2t and minus z square divided by 2. RT and minus RT we can cross, and we have these three terms, and you see if we write in the denominator 2, it is z, this z. We write in denominator 2, it will be 2 factor, and we can write minus before this fraction, and the fraction you see z square sigma square and 2 z sigma square root from t. Yes, so it is z plus sigma square root from t and bracket and square. So z square we have, sigma square t we have, and minus, no plus, it's minus because we write minus before this fraction, and minus double product of z and sigma square root from t. Yes, so it is our new variable z minus sigma square root from t. Um, yes, and but this it is the function integral function distribution from d1, and it's plus, it's this, it should be plus, and this is, it is function of normal distribution from d2, but how we can find this d1 and d2? It is, you remember that the call option win if the market price more than strike price. And now we would like to find the moment where the market price equals strike price. Market price we write like this according to our theorem. So we can solve this equation and find from this z. For this we find a logarithm for both sides. Yes, and it will be this expression, and after that, where is z? It is that, but these terms we write on the right side, and that equals you see these factors 1 divided by sigma, this square root, and into this. So it is a way how we can find the limits of these integrals. So we have the celebrated Black-Scholes formula, um, Nobel Prize in 1998. It is that the fair price uh, looks like this, and it is the cumulative normal distribution, and D1 and D2 in this formula we can find as this. Um, so we have a model for financial market, and on this financial market uh, we know the formula, the model for riskless assets. It is the formula of continuous compounding interest rate, and we have the formula for the risky asset. It is um, it is the formula according our theorem, and now it's called as geometrical Brownian motion. And this model we get using efficient market hypothesis. And we have formula for the fair price of derivative. In this case, you see the formula for call option, but in really we can get the formula for any derivatives, um, because actually Black and Scholes didn't use the Cox-Ross-Rubinstein model, because this model appears only no, after that. Mm. But Black and Scholes used this equation, and where f is fair price of any derivatives, and the initial condition and bounded condition define the what kind of this derivative. And if we solve this equation with initial and both condition, we can get the fair price of any derivative. This formula is called Black-Scholes equation. Um, so we have the formula for risky asset, and equation from defining any fair price of any derivatives.